Okay. So what I'm doing now, we're just using the fiber. So last year we just okay, great. So last year we deployed fiber in a CCS project in Abu Dhabi. So we record the zero offset and offset VSP every month, and we just finished the three-phase 3D VSP. So this is what we call 4D VSP because it's time-lapse. And we also finished largest acquisition showing the DAS VSP and the C acquisition in the UAE. And last year we finished another version. It's also the giant C and DAS VSP in Saudi. So, DAS VSP technique. This is what I just talking about. So this is a giant 3D seismic and DAS VSP acquisition. And this is a comparison between the geophone array and DAS VSP. So yes, compared to the traditional geophone array, this is a conversion types. We deploy the fiber cable in WLB and we deploy the geophone array in LA. So they're very near to the well. And we record the 3D seismic. So compared with the geophone, does have a very high density of data. And it deploys the fiber to the bottom of wall. So this is a full, what we call full borehole acquisition. Another thing, this is very high efficiency. Compared with the geophone deployment process, the fiber using less 1 day to finish the acquisition, finish the deployment. And compared with the geophone, the fiber is very cheap and it's will very low cost of operation because you save time, you save money. This is the data once you're using the acquisition by the geophone area and the fiber cable. As you can see here, this is the very high density because the sampling for the DAS is 1 meter. So DZ is 0.83 meters. And most of the VSP's record is good here, so very good quality of data. And one thing we're using the fibers to do the DAS VSP to component to make the surface seismic imaging very well. So this is what we call the precise borehole joined seismic data processing. So normally we join some of the parameter from the VSP, like the TAR, Q, and we're using the VSP's velocities modeling to compose the seismic, surface seismic. Yes, as here we using the dust recipe to derive the Q value. As you can see here, the dust recipe so have very high need and very compared with the geophone, the Q value will be very accurate than what we done by the geophone. And this is the vintage data. We put the two new wells fiber to record the dust VSD. And three old well, we have the geophone's VSD record. So we're using the Q value to component to do the full wells Q migration. This on the left hand side is from the Optical surgeries results. And in this way, we using the I think it's the application. Yeah, it's here. So this is the observation system of the Optical surgery. And on the right, we just perforate the dust entity to form the full well Q migration. So this is before the Q tunnel, and this is after Q tunnel. We using the combine the uphold data and the VSV data again. And after that, we can use this Q value to do the migration. On the left hand side is the vintage PSTM the result, and the right hand side is Q migration result. As you can see here, the frequency spectre is become wider, and the timing of the structure are very clear. And this is the coherence time slice. The same one. The left is the PSTM, and the right is the Q migration. And you can see here the structure is here smaller than the PSTM results. And this is the 3D dust VSD data processing workflow. We do the well-filled data. We just did some same, I think the same one as the normally what we do with the traditional VSD technology. Because dust is only the required method difference, but the thing is the data is the same. Geophone measure the velocity, but the dust measure the string rate. It's the same string or string rate. So this is an example of what we done 2 years ago in Abu Dhabi. So it's the largest world. Okay, thank you. Largest 3D OBN and dust VSD application. So as you can see here, this is two artificial. So island here, one island we have 6 well, and another one we have 7 well. And this is just those OBNs shape, and we do the air gas source, and we record with the OBN and dust system together. And you know it's very large project. This is it's blended acquisition. So the first things for dust, the one challenge is this is a blended acquisition. We need to do the blended precisely. And this is the on-site QC. So we're matching the GPS time from the source sheet, and we just to do the segment of the dust data, because dust record is continuous data. It's like the same way with the OBN, the node. And we can just slide the short the signal from the continuous dust data. And this is what we using only the VSP, dust VSP data to do the migration, the imaging, multiple imaging migration. So, and this is from the single imaging. And on the right hand side is the giant 5 wells imaging together. So I think this is very clear. So this is the vintage SLT RTM results. This is the perform across the wells LL 651. And this is the imaging result. This is the imaging result, the same the profile by the dust. Okay, this is by the dust. This is the legacy, the OBS dust imaging results. And this another is the perform. As you can see here, only using the dust data, I simply take the same the results, and you can just acquire the high quality of image because the dust data have a very high density. The same one. Another is perform, so it's crossed by the 7 wells. So this is you combine the 7 wells USB data to do the RTM image. OBC data results and dust results, OBC results. Join the OBN and USP, you can do the multiple ways imaging. So this is the when the OBN starts, and in the middle is red, and the right is so you just overlap the OBN results with that as the results. As you can here, thus will compose the OBN image results and will have a very clear of the structure. As you can see here. Yes, this is the thing. This is the result as depth slice 2000. Okay, the second part I will talk about the reservoirs monitoring technique. So this is like overlook the application of the productions using the dust technique. The first one, once you just put the fiber outside the tubing, you can just measurement the cement quality using the DTS. Because once you cement, the temperature will go up and then will cool down. The precise by DTS measurement can be evaluating the quality of cement. Another is you just put the fiber outside the tubing or the inside the inside the casing. You can measure the interface, oil and gas in the borehole. And dust can be also used in the fracture, hydraulic fracture to monitor the perforation and the fluid front injection, evaluate the fracture effect. And another, you're using the fiber deployment, Jackson well to monitor the check 3 by the perforation and the fracture. This is what we call LS, low frequency dust. And also, you can using the dust to do the production and the injection logging. And this is for another application in CCS, geo storage, and pipeline safety, and drilling. This is very important things because once you just drilling, they have to equate at some point. You put the fiber in the with the drilling rig, and you can just detect it very quickly using the dust monitor. The liquid point will very obviously detect by the dust. This is the perforation in the fractures precisely. So as you can see here, this is like the signal we record by dust. This perforation, signal 1, signal 2, signal 3, 4, 5. And the highway one, I think is the perforation, the bond, the perforation. And this is why this monitoring is good because this is in real time. Otherwise, if you're just using some other technique like the microcycling is also the real time, but the other things, some logging speed is after the fractures evaluation. And this is precise for the what we call the diversion. Once you have the perforation, so you need to want to inform the fracture in a network, not in one direction, but in many directions. So in this way, we just inject some agent or some plug, so ball to invert the direction of the fracture in another direction. So this is the way what we call the diversion. So using DAS, we can just have some results like this. So as you can see here, so the blue one is the right one is noise, and blue one is like square. So in this configuration, this is dash, this is tank. So this is the bubble, and you inject the fluid in this way, in the reservoir. And you can see here the noise will just focus on concentrated on the perforation location. And once you just stop the fracture process, the well will become quiet. And then you do this is the diversion. And as you can see here, this is that way. You want to just perforate this zone, not the default. So this is the leakage at top. Yeah. So you can see here. Yeah, let me do the say here. So we go to have the bridge in the end to isolate the lower the location. This is the bridge. And once this leakage, as you can see here, is the result, the noise will below this point. And why we can use that to evaluate the diversion? Before this is not open, this perforation, the first, second, and third one. After using the diversion, then you inject the agent. Some cluster will be just closed, and this one will be open. So this is what we're using that to monitor the fracture process. And after the fracture, we can use the results to evaluate the fractures precise and the results. So we're doing this, we can using the dust noise energy to calculate the volume of the injection. So in each cluster, in each perforation. This is what we cannot do before without dust. So before we're using the microcycling, we only have the draft results of the fracture network. But using that, you can see it's very tiny. You can using the dust monitor only 3 to 5 meters in this very small scale. And this is the results combine the dust and DTS results to evaluate the fracture results. So as you can see here, we using one parameter is called fracture uniform index. This is like you have several perforation. We want to every perforation is open and everyone has the same value inside. And the uniform index up to the minor than the 0.1 means this perforation is very good. Every cluster have something going. So you can see here, this is the before of the injection value. As you can see here, this is very good, but this one is not good because some cluster is not open. So without any injection fluid. And we also combine the optical fiber mountain with microcycling. So this is using geo4, because if you deploy the fiber cable in the gas well, you cannot monitor a lot of the microsatellite events because the cable is with very high in production. So this is the down the safety of the fiber. So the recording between the geophone and the fiber, the total number of the microsatellite events will be less than 10%. So compared to the geophone. This is the widely known now. So we're using the geophone to do the microsatellite monitoring, but not the DAS. And this is another technique what we call low frequency DAS monitoring. We also deploy the fiber in the jet mill. This is the fractal mill, this is the fiber mill. So after the perforation, the fluid will go inside this direction. And this is the fiber, the jet mill, this is the fractal mill. This is like the tensile string, and the others is the contract string. Once this string reach the fiber well, we'll have something that in the center is a tensile, and the both sides is a contract. After that, the fiber will close, and then the chain on the contrary in the middle will be the contact string. On the other side will be the tensile string. So this is the principle why the fiber using the low frequencies monitoring. And this is the real data of the field. As you can see here, this is what we call the hard signal. This is very typical fracture signal. As you can see here, we have 1 point fracture, and here we receive the signal at 0.003 points. This is not that the fracture will just operate in these 3 ways. Maybe in here it's not, only they have some natural fracture here, and this detection just to reactivate the natural fracture. Yeah, as we just in the field evaluation, only these 2 points as a fracture growth. And this is using the DAS and DTS to do the production and injection logging. As you can see here, we just record the temperature change for the full hole. You can declare any depth temperature change. This is the temperature change rate. This is in the perforation well as well. And after you do the data inversion of the DTS, you can just obtain the production perform. This is the production in the cluster, and this is total value. This is total flow rate. And this is the example of the DTS to evaluate the quality of the cement. As you can see here, once the cement injection and after the solidification, and they will release the heat and the temperature will increase. This precise, there are some points temperature not increase like this much. And we're using like this skewing of the depth, we can evaluate this is not good. This is not good cement, and this way is not, this is good cement. And this, I think, is some logging method can also be using for the cement quality evaluation, like sonic and sonic logging, another that's the radio logging. As you can see here, this is a perform of the moving interface, what we call the water ledge, because this is the pump. Well, they're using the pump as a 3 times salt or the 5 times salt. So this, as you can hear, is very clear. It's clear because in the fiber, in the liquid, and in the gas, they have different specific heat capacity. This will result very clear lines to calibrate the interface between the oil, between the liquid and gas. And if they have something like in the middle between the oil and gas, they see this is the power plug. It cannot be detected by the sonic logging, but it easily can be detected by the DTS, because DTS is very sensitive. And we're also using the DTS and DAS to do the injection optimization application. So as you can see here, we inject the 5 cubic meters. The DAS report will be like this, and we increase to the 3,000 cubic, and then as well as a response as a cluster like here, and then we increase as well to the 3,300, and something will be very intensive. Now as here, we do not do like this very intensive in some injection. We want to like post out the displacement in the van der Waals. So we need to each cluster have the same value. This is cannot be happened in the real, but this is what we just expected. So we do in this projection, we just selected the best injection system. It's like this. So after you using the DAS monitoring, you can have the results to do the optimization of the injection. Here we put the fiber and involve the gas storage well. So as you can see here, this is the leakage point. The temperature will just increase at this point. How they have some gas release. Gas release will display the temperature in the well, and it decreases at this point in the well. This is a paper, I think. Paper liquid. Finally, let me just draw the conclusion. So, DAS system acquire the seismic data has very many advantages, like low cost, high density, and full well coverage, and the fiber will have the high temperature resistance as well. And BGP can provide me like the several kind of DAS with the many fields, offstate, zero offstate that will work way or wrong, and join the 3D VSP with the surface activation. As DAS VSP, so is another way to aggregate the borehole seismic data. So compare with the GeoForm, DAS have very high density. This will be resulting in a higher resolution of the imaging than the traditional VSP and the surface seismic. And horizontal as well, with the arm outside the fiber deployment, can be monitored using in the hydraulic fracture operation and by the microseismic monitoring production and the injection monitoring as well. So simply all, this is all my presentation. So any question you can just thank you. Okay. Okay.
So you thought because I'm particularly interested in this kind of topic. And I have some questions.
Okay.
Can you explain me the difference between DAS and DSS? So for my tuition there.
DAS is as you can see the name, DAS is acoustic sensor, and DTS is the temperature.
No, DSS.
DSS. Okay. They have some different principle. The DAS is based on the principle radially backscattering.
Okay.
But DSS using the Brilliant scattering. This is a different principle. And as you can see here, I just showed, this is a presentation. I don't think it's very technical presentation, so I didn't explain more about the principles. If you are interested, you can just search in Google. The relay backscaling is dust principle, and brilliance backscaling is the DSS principle. And DSS is also called the DSS because brilliance backscaling is affected by the temperature change and strain as well. So this is what we don't want. So we're using the dust.
Okay, so DTS and DSS use the same cable?
Yes. In one cable, they have several units of fiber. We put like 4 fiber inside one cable as well. And the fiber have some different mode, single mode and multi-mode. You're using the dust, so single mode fiber. You want to have the relay backscaling. So relay backscaling is electricity backscaling. But if you're using the DTS, you put the fiber connect to the multi-mode. They can be more reflection inside the fiber. Yeah. The pathway is different. Single mode only one pathway, but multiple has many pathways.
Another question.
Okay.
And how makes the coupling that they are?
You need to record the.
No, I mean the coupling. How was the data mixed for displaying a seismic profile?
You need to compare with the seismic data. I don't understand. Sorry.
Well, I understand the seismic profile to show
Okay.
that they were enhanced
Yeah.
with that data.
Yes.
The DSP.
Yes.
How was that?
Because in high density, you have high density, high temperature rate. Does have the temperature rate with 1 millisecond, so simply for time, and 1 meter so simply. So you also in the time and in the depth, you have very high density data. And this is what we use in some processing method to enhance the quality of data. Yeah, if you want, this is not the only single sentence come after it. If you are interested, you read some technical book. I think this 2 years ago, the Willis from America wrote a book about the dust, dust acquisition in the exploration, especially in the West technique. Okay. Thank you.
The fiber that you use is really complicated design.
No,
Not so complicated.
No. The fiber, the structure, the same with we use in the communication in the fiber. It's the same, but the structure communicated is outside.
Okay,
Yeah.
yes, I mean external.
Yes, the
So
same.
it can combine. Yes, so my question is comparison with the other kinds of.
Yeah, the same. The fiber is the same as this one.
Yes, but considering the external part.
External part is complicated.
As you show, the design is
Yeah.
it's really hard and complicated.
Yeah.
So my question is, in comparison with other kinds of these kind of fiber, how expensive?
How expensive is
Is
it's highly related to the ball temperature. If we're using the high temperature resistant fiber cable, I think it's very expensive. But in the normal, I think it's not so expensive. We just finished a project in Colombia 1 week ago. We're just using one fiber cable. The one is we're using the fiber cable with magnitude. This is the absorption between the fiber and to the well of the wall. And another is just standard fiber cable. Is I think every 10 meters is only less than $20. Yeah. $20, yeah. But the shipment is another. We ship the fiber cable from China to here.
The question what about the interrogators? How much is the cost?
The integrator, yeah, it's very expensive. So, for us, we just do not sell the up to now the very high efficiency the emitters. So we have 3 generations. And right now we just sell the first generation. Yeah, here. So right now we only could sell the first generation and the second one, and not the 2.3 and just the second. And this is very expensive. It's like the $200,000. Yeah, 2,000 K. Yeah, the integrator is because of high tech. And so far, I think only two Chinese company and one Russian company using our integrator. Yeah. And you can look at another company. They are more expensive than us. Yeah, like the Silixa. Silixa is a British company. Yeah, they just have several generation of production. I don't know if some rejection in Colombia or not, because in China they have some production limitation of the new teeth one. They don't sell the new teeth integrator to China. Yeah, only in the US and British. They can supply the service, but they don't sell the production.
And well, in PGP, do you store all the data and ETL data?
Yes.
Like it has lots of storage. Memory.
Yes.
So, but it is what do you use it like dump samples or raw? And each data acquisition price like a lot of storage. So do you store it like some samples or just raw?
With you mean the data storage on site? Yeah, the data will have a large size of the document.
Yeah.
I think just finished the project last week. We acquired the TB level data. Yeah, and once we just first one we're doing the segmenting, slide the data to the source, and this will reduce the size of the data, and then we can just do some another setting work. And what do you need? You want to know the storage the machine?
No, I mean.
You can speak Spanish because my colleague has.
How do you handle with that big size of data?
Visibility. It's mystery. Thank you.
Bueno, muchas gracias a todos los asistentes y a todos los que estuvieron igual. Agradecer a Caneva, Orlando, la Universidad Nacional por el espacio que nos brindó. Queremos contarles que BGP es una empresa multinacional de origen chino, con como se mostró al comienzo, está en más de 54 países, tiene gran desarrollo en investigación y desarrollo, tecnología, queremos hacer, con la Universidad Nacional estamos haciendo por ahora un borrador de acuerdo para un convenio de cooperación institucional, cooperación que está muy bien en el Departamento de las Ciencias, la parte de geofísica, de traer tecnología a Colombia, y este es uno de los inicios que podemos tener conferencias y también tecnología práctica con ustedes. A ustedes muchas gracias, a todos los estudiantes que estuvieron y a todos los participantes. Esta es una tecnología muy avanzada en la parte para producción de petróleo y gas, y también para lo que se viene adelante, como es la inyección de gas o de inyección de CO2, o también la visualización más profunda del subsuelo y de integración de muchas herramientas. Aquí se conjugaron muchas cosas, que es tanto de adquisición de información como de modelamiento y de integración para entender el subsuelo. Les agradezco nuevamente y tenemos ahora un pequeño coffee para ustedes.
Sí, thank you very much for coming. So on behalf of our university and the Department of Geosciences, thank you very much, Mr. Hodjan. Thank you to BDP for sharing this technology with us. And we really hope that this kind of exchanging information will continue in the near future, and we will be able to continue this sharing. Thank you very much.
Thank you.
Our university.